TalentSprint. We are here today in our live session. We'll discuss about data structures. We'll try and understand data structures a bit more better in a very different way so that you appreciate and understand the use and importance of data structures in computer programming a little more. So we have a nice presentation ready for you. Let me just share the screen and start on with the session. So understanding data structures. Now we all might have heard of data structures during our engineering days or post-engineering while we are learning a new programming language. Well, if you check what a data structure is online, we get a very interesting definition of it on the wiki page that says, in computer science, a data structure is a particular way of organizing data in a computer so that it can be used efficiently. Now, very well said. But there are a few keywords in this. Number one, you are organizing your data. So there has to be some value and data with you that you need to organize in a particular format to access it properly. Okay? Now, before we try to understand more in depth of what a data structure actually is, it is very important to first understand what is a data type. So a data type is simply classification of data which tells the compiler or interpreter how the programmer intends to use the data. So the data which tells the compiler or interpreter how you as a programmer are going to use your data. Is it going to be an integer data? Are integer operations going to be performed on it? Or is it going to store some string, characters, etc., etc.? So the primitive data types like integer, boolean, real comes into it. Also some advanced data types. So in primitive data types, we have machine data type, we have numeric data type, we have boolean data type that would store only zeros and ones. While in composite data types, we have arrays, records, sets, etc., etc., etc. So all these come in composite data types. So data types are defined based on the value that they will store. And that in turn also defines the operations that can be performed on these data types. All right, so far so good. Now when we move to something known as abstract data types. What is an abstract data type? So an ADT is a mathematical model for data types, where a data type is defined by its behavior. It's going to behave as integer or character or boolean value that can only have two values, 1 and 0. So from the point of view of user, how is this going to behave? Especially in terms of possible values, operations on this data type, and the behavior of the operations. All these things determine what an abstract data type is. Okay? Now, data structures are simply the implementation of these abstract data types. Different kinds of data structures are suited for different kind of applications, and some may be highly specialized or specific tasks. For example, in a relational database, commonly uses binary tree to index for data retrieval purposes. Whereas in compiler implementations, you might see hash tables being used. So for different purposes, different data structures will be used. Now let me show you why actually we need data structures. Let's say in your room, you have your stuff lying around, you haven't cleaned up your room for 3-4 days. There are books lying around everywhere, clothes not properly kept, stationery and personal items not in place. Basically, everything is haphazard. Now, if someone asks you to go search for a particular shirt in this mess, no matter how efficient your searching is, the search process is definitely going to be very, very slow. And this is how you're gonna look like. Now, if the same room has everything in proper stacks and placeholders, clothes nicely folded or hanged in cupboards, and books properly stacked in the shelves, now, if someone gives you the same task of finding your shirt or maybe finding a particular book, it is going to be a much, much faster process than it was before. So you see, the search is going to be more easier and efficient if your data, in this case, your particular items of the room, are organized and arranged nicely. So data structures serve the similar purpose in computers. They provide a means to manage large amounts of data efficiently for users such as large databases and internet indexing. Usually, efficient data structures are key elements in designing efficient data algorithms and hence designing efficient programs. The implementation of a data structure usually requires writing of a set of procedures that create and manipulate these instances. So this is what about data structures, why they are used, what is the purpose of using a data structure in your computer program. The accessing of data and the manipulating of data and working on data is what we aim for while majorly writing programs, and this is what we gain from data structures. Now let's look at certain data structures. I'll go through a few of them and explain to you what are different data structures. So basic type of data structures, as we discussed above, anything that can store data can be called as data structures. Hence, integer, float, Boolean character, everything fall into a data structure because they store certain type of data. Now, they are known as primitive data structures. Later on, we also move to complex data structures, okay, which are used to store large and connected data. So some example of abstract data structures are linked list, tree, graph, stack, queues, etc. Let's take a look at a few of these. So linked list. Linked list is a linear data structure and it is very common data structure which consists of group of nodes in a sequence which is divided into two parts. Each node consists of its own data and the address of the next node and forms a chain. So linked lists are usually to create trees and graphs. So as you can see in the image, there is a header that contains data and address of the next node. Now the next node again contains its data and address of the next node. So there are different types of linked list. Single linked lists contain nodes which have a data part as well as address part, that is next, which points to the next node. And the operations we can perform on single linked list are insertion, deletion, and traversal. So we can insert data, we can delete data, we can traverse through this data. Next is doubly linked list. Now in a doubly linked list, each node contains two links. The first link points to the previous node and the link next points to the next node in sequence. So now you can go back and forth as well. You can go to the previous node, you can go to the next node. Also, we have circular linked list. Now, what is different in circular linked list is the last node of the list contains the address of the first node and forms a circular chain. So when this chain is formed, a linked list is called a circular linked list. Now, moving on to stacks. So allowing adding and removing elements in a particular order is what stack does. Every time an element is added, it goes on top of the stack. and the only element that can be removed is the element that is currently at the top of the stack, just like the pile of objects. All right. So as you can see in the diagram, there is a stack and there are elements entering at the top and being removed from the top. So every time you add an element, the top will move to the added element. If you remove that element, the top will move back to the previous element, pointing out the top of the stack at any point of time. All right. So basic features of stack. It's a last in first out structure, as we saw. So an element that has to be added will be last in and removed will be first out. And the operations that insertion and deletion are referred to as are push and pop. So insertion is called push and deletion is called pop. Now stack doesn't have a fixed size and it doesn't consume a fixed amount of memory. So as you see in this diagram, we have shown the push operation. The element is going in and the top is moving up to the element that is being added, that is E. And similarly, in the pop operation, if the element E is removed from the top of the stack, the top will point to the next element, that is D. So every time you write maybe a program to do insertion and deletion of stack, make sure you make your top move when you add or delete your elements into the stack. Now, moving on to trees. Now, a tree is a data structure made up of nodes of vertices and edges without having any cycles. So as you see on the right, there is a node shown that points to itself. This will not be referred to as a tree. While on the left hand, we have a node A pointing to a node B. So that is a tree structure. Tree with no nodes is called a null or empty tree. Tree that is not empty consists of a root node and potentially many levels of additional nodes that form a hierarchy. So for example, if you start making down your family tree, your grandparents, then your parents, then your uncles and aunts, then you and your siblings, the family tree can be very well represented in a tree data structure. All right. Now, there are a few terminologies that are generally asked in exams, so you should be familiar with tree terminologies. So root is the topmost node of a tree. The child is a node directly connected to another node when moving away from the root. So if your root has two elements, those two elements are the child of root. Parent node is the converse notion of child. So let's say you have root node A and B and C are the childs. So A is also referred to as the parent of B or the parent of C. Now, B and C, since they are the child of the same parent, they are also known as siblings. Okay? It's exactly referring to your family tree, so you can correlate and understand it better. Descendants, a node reachable by repeated proceeding from parent to child, is known as descendant. So if your grandfather, then your father, then you, so you are the descendant. Now branch internal node, a node with at least one child, is known as branch internal node. Leaf node, also known as external node, is a node with no children. So if there is no further branching out at a node, then it is called a leaf node. Then ancestors, a node reachable by repeated proceeding from child to parent, is called ancestor. The number of subtrees of a node is called the degree of a particular node. The connection between one node and another is called edge. So whatever connection you have between two nodes, that is referred to as edge. Now what is a path? A sequence of nodes and edges connecting a node with its descendants is known as path. So there can be sometimes only one single path to reach a particular node from the root node, or sometimes there can be more than one path to reach your destination node. Moving on, we have level. So the level of a node is defined by 1 plus the number of connections between the node and the root. So you find the number of connections between the node and the root and you add 1 to it. That is called the level of the node. Height of the node. Height of a node is the number of edges on the longest path between the node and leaf. So if leaf is like 4 nodes down, the height of the node is 4. Height of tree. So this we talked about height of a particular node in the tree. Height of tree is the height of its root node. So when you calculate the height of root node, you get the height of the tree. Depth of a node is the number of edges from the tree's root node. So when you calculate height, you take it from the leaf node, but when you calculate depth, you take it from the root node. Okay? Now, Q. Q is an abstract data type. The first element is inserted from one end called rear, also known as tail in some places, and the deletion of existing elements takes place from another end called front, also known as head. So unlike the stack where last in is going to be first out, in queues, first in is always going to be first out. The process to add an element in a queue is called NQ, and the process to remove is called DQ. So in stacks, we understood that insertion and deletion is called push and pop. But in queue, insertion and deletion is NQ and DQ. Okay? So it's fairly simple to understand the basics of data structure, Rahul. First off, you need to understand, like I pointed out in the very beginning of this session, why a data structure is actually used. So when you understand why it is used, what is the need of data structures, why it came into the picture, it will help you understand the rest of the data structures even better. So let's say you have to understand about, let's go back to maybe stacks, all right? And assume that this is the first time that we are talking about stacks. So we see stack is a data structure which is used to store data, number one. Number two, we are storing our data in a particular way. So data could be a list of numbers, a list of words, a list of characters, whatever data you have to store. Okay, this is your storing process, implementation process. So you want to store your data in a way that the new element that comes in gets on the top. And if someone wants an element, he takes it from the top. Okay. If your implementation requirement at any point of time while you are writing a code or while you're programming is this, that is the time when you use a stack. So take any real life example where this would happen. Let's say your mom is cooking chapatis at your home. So she cooked a chapati, she put it in the hot case, and then the next one goes on the top. The next one goes on the top. So the new element that is being created goes on top. And now when it is being consumed, the topmost element is taken up first. Then the next, then the next. So that is a very vague real life example that I'm giving you of some implementation of stack. Try to correlate your data structure with real life. That will be easier for you to understand if this is the first time you're understanding. Grasp the basic of why which situation this data structure would be used in. And then the implementation and the understanding process comes very easy and becomes very easy to understand. So now you understand the push pop top for a stack, I hope. So now let's go back to queues. So now as in stack, we are adding at the top, removing from the top. Now a queue, let me show you. the diagram. The queue is something like this. The data is going in from one end, but it is coming out from the other end. So if say you first put an element called A, then you put B, then you put C. Now if you want to delete an element, A would be deleted first, then B, then C. You cannot go ahead and delete C. So this is first in, first out. The data member that goes in first is the data member that is coming out first. Fairly simple to understand. So a queue, if you want to represent this data structure, if you want your data to be in this very format, you can implement it using arrays, using pointers, using structures. But you need to remember that first in is going to be first out. So the process of insertion, these are the terminologies that may vary. Like in stack, it is push-pop. In queue, it is NQ and DQ. So these terminologies vary for different data structures based on what the functionality of these data structures is. Okay. So here we NQ when we push an element and DQ when we pop. Now, in stack, we maintained one single pointer called top because insertion, deletion, both were happening at the top. So we had to manage only that top pointer. But in queue, since insertion and deletion happens at two different ends, we need to manage a front and a rear. So when you insert at rear plus 1. When you delete, you take care of it using the front. Alright, so this rear and front concept come into picture because insertion and deletion is done by two different places. So I hope you understand the difference between stacks and queue. Now, similarly, tree is very different. Trees, as I said, match it up with your family tree. So the root and child and then grandchild, that is tree. So if some data you think needs to be stored in that format and will be easier to access using that format, you use trees. Now there are certain data operations that come along with these data structures. So depending on that also, you can choose which data structure to use in your program. All right. So basic operations here are NQ and DQ. And along with this, I hope we understood here that why are data structures so very essential in programming. And also, what is the difference between stacks and queues? Where do we use stacks? Why do we use queues? What is the use of a tree in our programming language? So I hope this debunked a few basics of data structures for you all. Now there are many different data structures. Like here also we took a look at trees, for example. So tree is also a very important data structure. Stacks and queues I'm referring to because of the similarities or dissimilarities, I should say, between how the values is inserted and how the values is deleted. So tree is also a very important data structure. It's not about importance actually, it is about what your requirement of program is going to be. Okay? Let's say stack or linked list we saw. Linked list is also very essential and important data structure. Now, linked list is, since we saw of three types, single linked list, doubly linked list, circular linked list. So depending on what you want to implement, you choose which particular linked list you want to use. It's up to you. Okay. So Balaji Deva is asking how to be master in C language. Balaji, it's very easy to be a master in any programming language, I would like to say, because it's all about how much passionate you are about learning the language. Even if you give like an hour to your programming practice every day, I think you can master the C language in about a month. You just need an hour of constant, disciplined practice towards C language. It's fairly simple and easy. Be it C, be it Python, be it Java, anything you want to start with. It's fairly simple to go ahead and, plan your understanding of language. Start off with the very basics. Keep, keep. I cannot stress any more on this. Just keep practicing and writing programs on your own. Keep running programs. Maybe you will encounter 100 different, issues while you're writing a program. Maybe the first day you sit on your desk and you write your first C program, there can be 10 errors in the program. But if there are 10 errors, you realize that you are learning 10 different things not to do when you write a program. Okay? These are the mistakes that you learn from. These are the mistakes that will make the understanding of the language better for you. Okay, so don't be afraid of making mistakes and don't lower your self-esteem if the first few days your practice isn't going very well. Just keep writing as many programs as you can, because that is all that is going to be rewarding at the end. Keep learning new concepts every day, keep writing more programs every day, and it's going to be a very easy process. So Ajit is asking, can we implement data structure algorithms in any programming language like C, C++, and Java? So data structures are implemented in almost all the programming language. Like I said, integers, floats, booleans, these are also type of data structures, right? You are defining that you have to store a decimal value and you have to perform operations that can be only performed on decimal values. So you take those decimal values and you store it in float. That is where, again, you're defining your data structure. That this particular float variable, let's say XYZ, is going to store a float decimal number. And then you define the operations also, that since it is a float, only these operations will be defined. Or if I do these operations on a float, this is the expected output. So that is a very primitive data structure that is implemented in every language. Similarly, all other data structures like stacks, queues, whatever, are also implemented in all the languages that you might learn in the future. Let's say you are going to learn C or C++, Ruby, Haskell, Java. Data structure. Think of data structures as a medium to access your data and store your data with perfection. So when your data is stored and accessed nicely, your program is going to be much more efficient. All right. So I think there are no more questions. I hope you enjoyed the session and you understood the concept of data structures fairly in a different light and made this very interesting for you to deep dive into data structures more easily. So enjoy your coding, keep practicing. As I said before, don't ditch your practicing if you're not okay. Keep making mistakes. Don't even worry about the mistakes you're making because they will only make you stronger. Happy coding, guys. I'll see you in the next session soon. Thank you and bye-bye.